Okay, here we go. 2016, number one. All right. So on 2016, number one, it looks like we're given a table. There may be an equation in there somewhere that we may need to use. So the first thing that I've done, as you can see on my calculator, is I typed in that equation that we'll be needing somewhere maybe along the way, and I put that into Y1 on my calculator before we even got started. Okay. All right. So we have this table, and now the problem. Water is pumped into a tank at a rate modeled by W of t equals 2,000 e to the negative t squared divided by 20 liters per hour for t between 0 and 8, where t is measured in hours. Water is removed from the tank at a rate modeled by R of t, where R is differentiable and decreasing from t between 0 and 8. Selected values of R of t are shown in the table above. At time t equals 0, there are 50,000 liters of water in the tank. Estimate R prime of 2. Show the work that leads to your answer. Indicate units of measure. All right. So, estimating R prime of 2, remember a derivative is just a slope. So for part A, what we're going to do is just find the slope as close to 2 as we can. If we're looking at the table, 2 is not in the table. Instead, we're going to pick the values that are around 2. Okay? So we're going to use R of 3 and R of 1. All right, so R prime of 2 is approximately equal to R of 3 minus R of 1 over 3 minus 1. So it's going to be something divided by 2 here. Let's see, R of 3 is 950. And R of 1 is 1190. Whoops. Okay. Because the calculator is allowed, I'm going to let the calculator do the work for me. Remember to type in a fraction, alpha y equals number 1, and then 950 minus 1190 divided by 2. So negative 120. This is approximately equal to negative 120. And now we need to indicate units. Okay, like it says, it does say to indicate units of measure. So R is measured in liters per hour. And the time in the denominator, the T, is measured in hours. So liters per hour. So this would be liters per hour squared. Okay? Or you could just leave it as liters per hour per hour. Either one would be fine. Okay? Part B. Use a left Riemann sum with the 4 subintervals indicated by the table to estimate the total amount of water removed from the tank during the 8 hours. Is this an over or an underestimate of the total amount of water removed? Give a reason for your answer. So a left Riemann sum from 0 to 8. So what we're going to do is we're going to take the integral, or we're going to approximate an integral from 0 to 8 of R of t. Okay, dt is approximately equal to now a left Riemann sum. So if I'm looking at my table, okay, so the first interval is from 0 to 1, but we're going to use the endpoint on the left. So it'd be 1340. So that's a width of 1 times 1340, plus the next one is between 1 and 3, and we're going to use the number on the left. So it has a width of 2, and it's 1190, plus, it does say with 4 subintervals, so far so good. And then from 3 to 6 is a width of 3, but the number on the left, the function value on the left is 950. So it'd be 3 times 950. Plus, and then the last one here, between 6 and 8 is a width of 2, but a height of 740. So 2 times 740. Okay? And then we're just going to use our calculator to add these together. So let's see here. 1 times 1340 plus 2 times 1190. I see that I have something bad at the beginning of this, but I'll go back and delete it. Plus 3 times 950 plus 2 times 740. 2 times 740, 3 times 950, 2, 1190, and let's see, 1. This should just be a 1 times 1340. And we should get 8050. So this is 8,050 liters have been removed. Okay. If we take the integral of the total rate that's being removed, then we'll end up with all that's been removed. Okay. And then it says, is this an overestimate or an underestimate of the total amount of water removed? And then give a reason for your answer. And so R of t, is that increasing or decreasing? So let's take a look back at the paragraph and see what it says. It says that R of t, where R is differentiable and decreasing. Okay, R of t is decreasing. So if we think about what a decreasing function would look like, it looks something like that. And if I'm using a left Riemann sum, and I just drew in a random rectangle here, using that left endpoint would be an overestimate. R of t is decreasing, and using a left Riemann sum would be an overestimate. Okay, so that's for part B. Okay, part C. It says, use your answer from part B to find an estimate of the total amount of water in the tank to the nearest liter at the end of 8 hours. Okay, so for part C, if I want to know the total will be approximately equal to how much we started with, and it says that at time t equals 0, there are 50,000 liters of water in the tank. So we're going to say 50,000 plus the amount of net change. Okay, so this is going to be the integral from 0 to 8 of the water that's being pumped in. So water is being pumped in, modeled by W of t. So water is coming in, so that's a positive rate, minus the rate at which it's being pumped out. So that's R of t. And we can kind of break this up a little bit, maybe make it easier to think about. But your properties of integrals, say if you're just subtracting these two functions, we can break them apart. So the integral from 0 to 8 of W of t dt minus the integral from 0 to 8 of R of t dt. And like it says, we're going to use our answer from part B for our calculations here. And in part B, we already found, or we approximated the integral from 0 to 8 of R of t, and we found that that was 8050. So we're going to plug that value in. So 50,000 plus the integral from 0 to 8 of W of t dt minus 8050. And this is just a calculator. Okay, we already have W of t in our calculator as y1. So on my calculator, I'm going to take 50,000. 1, 2, 3, 4, yep. Plus the integral, so math 9, from 0 to 8 of my out function. So that was y1, right? That's the rate at which water is being pumped in. I hit the wrong button. Alpha trace y1 dt, or dx in this case, minus 8050. And so I end up with this. And does it say, use your answer to find to the nearest liter. So this is going to be to the nearest liter. So I'm going to need to round this. And if I rounded this, it would be 49,786, right, liters, okay, at the end of 8 hours. Okay? All right. Oops. Okay, so for part D, is there a time t when the rate at which water is pumped into the tank is the same as the rate at which water is being removed from the tank? So I want to know, does W of t ever equal R of t, the water in, does it ever equal the rate at which it's being pumped out? Okay, so what we can do is we can kind of rearrange this, maybe make it a little more sense. What if I took W of t minus R of t and set it equal to 0? That's what I'm essentially trying to figure out, is where is this difference 0? Okay, so let's think about at 0, at t equals 0. Okay, so w of 0 minus r of 0. Let's figure out what that equals. All right, so r of 0 is 1340. So on my calculator, I'm going to find w of 0, and I'm going to subtract 1340. Okay, something's not right. Oh, I forgot a parenthesis. Okay. All right, let's try this again. Y1 of 0 minus 1340. So that's a positive number. We could give it the actual number, that's fine, 660. And then let's talk about at the end of the interval. So w of 8 minus r of 8. Okay, let's see. Y1 of 8 minus r of 8, which is 700. That's a negative number. And I'm not too concerned about what the numbers actually equal. My main concern is, did I get a positive and did I get a negative, right? Because if I'm positive at the beginning of the interval and I'm negative at the end of the interval, right, then that means I have to equal 0 somewhere in between, right? In order to go from positive to negative, as long as I'm continuous, then I have to equal 0, right? In order to go from a positive to a negative, you have to equal 0 somewhere, okay? So let's see here. Let's start by saying that w of t minus r of t is continuous. Because it's continuous, we can apply the intermediate value theorem. Okay, and the intermediate value theorem guarantees, the IVT guarantees at least one time t for t between 0 and 8 such that w of t minus r of t is going to equal 0, or we could say w of t equals r of t, okay? So in that case, the rates being pumped in are the same as the rates being pumped out. Okay, let's talk about the points real quick on this one. For part A, you get 2 points, 1 point for your estimate, 1 point for your units. For part B, you would get 3 points for this one, 1 point for your sum, setting it up, 1 point for your estimate, 1 point for identifying it being an overestimate. For part C, you'd get 1 point for your integral in this expression, and then 1 point for your estimate. And then for part D, considering w of t minus r of t, or thinking through that process, and then 1 point for IVT and its explanation. Okay? All right.